In this episode, an incredible rail network driven through London's historic heart.
The new Crossrail trains will carry 200 million passengers in and out of London every year. It's very exciting.
Pushing urban construction to its limits.
These machines allow you to pump 60 tonnes an hour. It's quite an art to see.
And the innovative pioneers of the past.
It's amazing that they were able to build this bridge in this torrent.
I love the Industrial Revolution.
That made the impossible possible. London, one of the world's most populated and densely built megacities. This mighty metropolis covers an area of nearly 1,600 square kilometres. But now home to almost 9 million people, with a further 31 million visitors each year, this cosmopolitan capital is grinding to a halt. It's a problem that engineer and commuter Camilla Barrow experiences every day.
London's a fantastic place to live. Everyone wants to be here. There's a lot going on. However, catering for these people in terms of transportation is critical, and as you can see right now, it's bursting at the seams.
Every day, more than 11 million journeys are made on London's transport network, including 3.5 million on the London Underground alone.
The current London Underground is about 150 years old, and it's a fantastic system and caters for a large capacity. However, it was never anticipated that it would cater for this amount of people.
To solve this seemingly insurmountable problem, engineers have embarked upon Europe's biggest construction project. "10,000 workers spread across 40 different construction sites are creating a brand new rail network straight through the capital's heart. For Operations Executive Michael Bryant, this project presents a series of complex challenges.
London's infrastructure is 300 years old, and underneath London is a veritable labyrinth of tunnels for all sorts of purposes. It literally looks like a hairnet that's been screwed up. It's extremely complex. Lots of the buildings now, particularly the large buildings like the Shard, have piles that go down 20, 30 or even 40 metres down into the chalk level. So it really is like threading a needle.
Stretching 118 kilometres, the network will pass through 40 stations, from Reading and Heathrow in the west to Shenfield and Abbey Wood in the east. Featuring an astonishing 42 kilometres of freshly dug tunnels, intricately woven through the existing underground rail system and deep building foundations of this complex subterranean world. In 2012, 8 gigantic 1,000-ton tunnel boring machines operating 24 hours a day, 7 days a week, begin creating this new network.
Right now, Crossrail is a mega project. It's very complex. It's costing approximately £15 billion.
It's probably the type of challenge that a civil engineer would dream of through most of his or her career.
And not only do these engineers need to find room for 42 kilometres of new tunnels, but also create space to accommodate 10 brand new stations. The most vital of all will serve one of the world's leading financial districts, Canary Wharf.
One of the biggest problems when we wanted to bring Crossrail to Canary Wharf was finding the space to do it. All of the land is full, as you can see up there, so the only place to do it was in the water. The challenge was to deliver a concrete box 28 metres below water level. The option of failure just did not exist.
So, how do you create a brand new station deep in the water of the River Thames? To realise that seemingly impossible challenge, engineers would take inspiration from some of the greatest innovators of the past. Travelling along Rome's River Tiber, Professor Rees-Morgan is in search of an ancient structure that has withstood the power of nature for millennia.
Oh, wow. It's amazing that they were able to build this bridge thousands of years ago in this torrent. Oh! Oh!
Constructed in 62 BC, the Pons Fabriciusa is the oldest Roman bridge still standing.
Oh, wow, that was fantastic. I'm totally soaked. There's a real strong current there. The foundations must be extraordinary to deal with that river.
Thousands of floods, earthquakes, countless wars, and millions of horses, carriages, and people have all put pressure on the foundations of this bridge. But still, it endures. It was commissioned by Lucius Fabriciusa, the curator of roads, after the previous wooden bridge had burnt down.
The very core of the bridge, the foundation in the centre, is where the clever bit happened almost 2,000 years ago. Unable to simply stop the river and drain the water out so they had a dry environment to build on, the Roman engineers had to come up with a revolutionary method of building while the water was in full flow.
What they designed was ingenious. It's known as a cofferdam.
The cofferdam first required a ring of timber piles that were bound together, driven into the riverbed. A second larger diameter pile of posts was then added to encircle the first. The gaps between the piles would be filled with clay to waterproof the central enclosure. So they had to pack the clay all around really densely, and then when they were happy, they would remove the water from inside the inner ring. Look at that. It's really working. And now I'm down to the riverbed. When all the water was removed from the inner ring, the builders could start working on the foundations. I'm going to use this stick as the central pier, and there you go. Fantastic. Once the foundations were built and the pier could be put in place, the cofferdam could be removed and the rest of the bridge could be built around it. And there we are, Roman engineering at its best.
The ingenious use of a cofferdam at the Pons Fabriciusa means this 62-metre bridge still stands as a testament to Roman innovation.
When it came to building solid structures in the water, Roman engineers really did make the impossible possible.
The engineers at Canary Wharf in London take the Romans' cofferdam and employ it on a gigantic scale. To build a brand new 250-metre-long station in water, engineers drive nearly 400 18.5-metre-long tubular steel piles into the dock floor to create a state-of-the-art cofferdam, vastly bigger than that used at the Pons Fabriciusa. But constructing it isn't without its challenges, especially when leading financial institutions with sensitive trading floors are your neighbours.
The traditional method of creating a cofferdam is actually to hammer steel members into the ground. And as you can imagine, that makes a lot of noise, a lot of vibration, creates a lot of dust, major disruption. So we had to come up with something that was better.
The answer to their problem is a brand new technique of silent piling. Instead of hammering the piles, a state-of-the-art Japanese machine called a Gaiken is used. Weighted to the dock bed and using powerful hydraulics, it silently twists and pushes the first 3 piles into the ground. It then crawls across and secures itself to those piles, using them as anchors, before pushing in the next one. This process is repeated until the cofferdam wall is complete.
We went for the first 3 years of the project without a single complaint from any of the neighbours.
Once the cofferdam walls are in place, engineers can begin the mammoth task of removing the water.
Over the next 5 weeks, we progressively took out 98 million cubic metres of water from the cofferdam, and that's equivalent to 40 Olympic swimming pools.
300,000 tonnes of material are then excavated, until finally engineers reach a solid foundation, 18 metres below, from which to begin construction. When fully operational, this £500 million station will be one of the largest and busiest on the new network.
So we have 4 floors below water, a floor at water level that we call promenade, and then there's 2 floors above and a roof garden.
At maximum capacity, 24 trains an hour will carry a staggering 68,000 passengers a day across the network, quicker than ever before.
To deliver this station ahead of time and within budget is a monumental achievement, and we're helping London take the next step forward.
But creating this mega station is just part of the £15 billion project. To complete the network, engineers will need the innovative trailblazers of the past.
For centuries, Dieppe had significant maritime importance. French explorers have left here to travel the globe.
To help create more impossible engineering. Deep below the surface of the UK's capital city, Europe's biggest construction project is underway. 42 kilometres of tunnels and 10 brand new stations, threaded through a complicated and busy subterranean world.
Crossrail will enable an extra 1.5 million people to enter or be within 45 minutes of central London. It's a fantastic project. You're working with some of the top expertise in the industry. It's very exciting.
But creating a colossal new railway above and below one of the planet's most densely packed cities throws up significant engineering challenges.
The most obvious issues with building a project as large as Crossrail within central London is working around this massive infrastructure that's already in place. We've got people living here, people working here. So we aim to really minimise the amount of disruption to the people, the noise, vibrations.
Carving out this labyrinth 40 metres underground requires 8 £10 million supersized tunnel boring machines, each 23 feet in diameter and as long as 14 London double-decker buses. For project manager Jules Boyd, making sure London's infrastructure and residents remain unimpacted by these enormous excavations are top priorities.
One of the constraints on the Crossrail operation, which is a massive operation, is to virtually pass by unnoticed to our neighbours. This is Finsbury Circus, a little oasis within the City of London. The buildings around us are old, they're sensitive, some of them are listed.
When the tunnels are dug, problems can occur as the surrounding earth resettles, causing cavities or settlement troughs to appear. If the settlement trough increases, a building's foundations could shift, causing structural damage.
This is a real historical centre of London, and it has to be protected.
So how can engineers keep these ancient buildings safe? It's a challenge that would require some inspiration from the great innovators of the past. Tunnelling under cities isn't new. In the 6th century BC, to have a supply of fresh water that couldn't be cut off by enemies, the residents of the Greek city of Samos dug underground aqueducts.
They must be getting thirsty by now. Cheers!
The soft volcanic rock beneath Naples meant huge networks could be dug for businesses, churches, and even a theatre, where Emperor Nero is said to have performed.
Ooh, he's on fire tonight.
Limestone mining under Paris created tunnels for what would become the world-famous catacombs, where the bones of 6 million former inhabitants now reside.
Uh-oh. Hold on! Push!
But any city excavation comes with a risk.
Ah, Luddy's better.
Farewell and adieu to you, oh Spanish ladies. Farewell and adieu to you, ladies of Spain.
Dr. Rhys Morgan is heading offshore for a seaman's view of a port with a surprising history.
That is one optimistic seagull. There's nothing for you, my friend. Behind me, on this lovely winter morning, is Dieppe Harbour on the northern coast of France. For centuries, it's had significant maritime importance. French explorers have left here to travel the globe. But since about the 11th century, almost 1,000 years, it's been a major fishing port.
But in the early 1800s, access to the harbour was under threat.
I've got a couple of maps here of the old harbour, and it's changed significantly over time. But what I'm looking for is a particularly important sluice gate that helped the big ships come into the port behind me. It must have been just about here, because as I walk around, I can see from the old buildings we come to much more modern buildings, and it's really open. And I imagine it would have been just around here. This large sluice gate would have opened, allowing the ships to come in and out of the harbour.
The gate had been constructed to stop the build-up of silt and pebble deposits, and was a vital tool in keeping the harbour entrance clear.
It was around about the end of the 18th century that the sluice gate stopped working, and this had a real impact on the economy.
The gate foundations no longer held their weight, causing them to stop working. Luckily, in 1802, French civil engineer Charles Berigny, employed to manage the harbour, had an inspired idea.
So this is my demonstration of the sluice gate and the problem that was happening underneath. First of all, we had the rocks on the bottom of the seabed. On top of the rock was a softer top layer. And it was on top of this softer top layer that the foundations of the sluice gate sat. Now the problem was that the water coming in through the harbour was going underneath the foundations of the sluice gate, and it started washing away and eroding the softer particles of the top layer. And that meant that the foundations of the sluice gate would be destabilised, and ultimately the sluice gate stopped working. Berigny's solution to the problem was brilliant. First of all, Berigny drilled a series of holes 5 foot deep through the foundations of the sluice gate down into the soil where it had eroded away. And then, this was the really ingenious bit, he got a piston pump, what he called a blow pump, and he filled that with clay grout. And with a series of hammer blows, he forced the cement down into the soil below. This is getting a bit messy, so I'm just going to squeeze it. Down you go, in you go. The cement's pouring through the holes, filling up the subsoil below, and making those foundations nice and stable.
As Berigny's clay grout was hammered through the pre-drilled holes, it spread out beneath the masonry foundations, squeezing into and filling the gaps created by the erosion. After a period of time, the grout set hard.
Okay, we've left it a while. We're going to see how it's set. Wow, it actually has worked. God, I really didn't think it was going to work, but that's fantastic. And unlike the soil, which was washed away, because it's solidified, it just stays in place. and that would have really helped the foundations of the sluice gate.
After minor tweaks to the technique, the grouting was completed, and the work proved a resounding success.
This was the very first example from Charles Birigny of injection grouting, and it's used in civil engineering projects all over the world today. Fantastic.
Engineers at Crossrail have taken those early injection techniques and developed one of the most sophisticated systems in the world, one which begins above ground.
Up on the corner of this building, there is one of the many ATSs. There's another one up here, and you'll see targets. These are essentially prisms.
High-tech surveying instruments known as automatic theodolite systems, or ATSs, are placed strategically across the city. The ATS fires a beam of light at its reciprocal prism. Engineers use specialized computer software to continuously measure the angle of the beam. If the angle changes too much, this can indicate a shift in the foundations.
If any of these points starts moving, then the grouting program can be tuned to actually compensate for any settlement.
Below the ground, in a purpose-built grouting tunnel, the team are busy reacting to recent information received from the ATSs above. At 3-meter intervals along the length of the grouting tunnel are a series of injection pipes that fan out above the construction work and below the delicate buildings. Getting the grout to where it's needed is the job of Principal Engineer Cliff Kettle.
So grout comes via the injection line from the piloted pump. Will come up this borehole. We'll isolate the individual sleeve. This rubber sleeve will push open. The grout will exit here and fracture the ground, and it will go into the ground.
As the injection rods are pushed into position, up to 25 litres of grout at a time are forced out through the rod and into the fissures of the ground, ultimately levelling the foundations and lifting the building back into place.
Some of the facades of these buildings here are 70,000 tonnes. We see on a daily basis that just the injection of maybe 3 or 4 cubic metres of grout can move that building several millimetres.
Spanning 5 years, it's the biggest compensation project the world has ever seen.
Compensation grouting is absolutely vital for the project because it does something that there is no other process for. There are many locations across Crossrail where the excavation couldn't have been completed without the protection provided by compensation grouting.
Excavating tunnels safely is one thing. Converting them into a high-tech rail network provides a greater challenge, for which engineers would need to draw on innovations of the past.
What incredible feats of engineering!
To produce more impossible engineering. In London, engineers are achieving the seemingly impossible. Weaving a brand new rail network over and under this city's congested core.
Crossrail is a fantastic project. Every day there's a new challenge, there's a lot going on, a lot to keep you stretched, a lot to keep you interested, and a lot of big problems to solve.
And one problem in particular is keeping project manager Jules Boyd especially busy. Throughout the network, a large proportion of the running tunnels have been excavated by the purpose-built tunnel boring machines.
The TBM's obviously a big machine, it's a factory, it builds segments of one size, it's building very fast.
As TBMs dig, they automatically line the freshly exposed clay with prefabricated concrete slabs, quickly shoring up and sealing the walls. But when they arrive at a station, these massive machines have their limitations.
It's not very flexible in terms of size, it will build one size tunnel only, which is what it's made to do. platform tunnels here, for example, 10 metres in diameter. You would never do those. They're 250 metres long with a TBM.
To dig these varied cathedral-like spaces, engineers have turned to the more conventional excavating machines. But if the freshly exposed clay is left unlined for too long, it could collapse. So how do you quickly shore up the more complex and cavernous spaces across the network that aren't automatically lined? To do that, engineers would need to draw on the work of an unlikely innovator. At the famed Natural History Field Museum in Chicago, science administrator Mark Alvey is discovering how one man's passion for preservation helped create a revolutionary engineering tool.
These are the Field Museum's famous fighting bull elephants. They were mounted over 100 years ago, and they're still one of our most iconic exhibits.
Created by explorer and so-called father of modern taxidermy Carl Akeley, they mark a milestone in natural history display.
Carl Akeley was the museum's chief taxidermist from 1896 to 1909, and he experimented with various sculpting techniques involving clay and plaster. His techniques were really revolutionary.
Not only did Akeley want to display the animals in lifelike detail, but their surrounding environment too.
And the techniques that he used in creating artificial rocks, like the ones you see here, eventually led to an innovation that would really have a huge impact on the engineering world.
It was during his search for lifelike perfection that Akeley came up with a new way of covering fake rocks with plaster of Paris.
So here we have a small rock that you might see used in a zoo enclosure. You can see that if we were to try to paint it by hand, it would be very tiring and end up with very uneven results. Now if I use my gun here, you can see you get a much more even consistency. It goes on faster. You can cover your surface much more quickly.
Then housed in a different building, the museum's director asked if Akeley could make something on a bigger scale to fix the museum's crumbling walls.
Akeley loved a challenge, so he set about creating a new plastering machine.
Initial attempts to shoot out hydrated plaster under pressure and over distance clogged the hose. Then, Akeley came up with a game-changing solution. He devised a way of shooting dry plaster through one hose that would meet a jet of water under great pressure in another, mixing at the nozzle. Akeley had created the world's first cement gun, and he went on to plaster the exterior of the museum.
The cement gun was soon modified, improved, and adapted for all kinds of industry and to create animal enclosures in zoos.
What Akeley achieved would be a template for all modern cement guns across the world, emphatically transforming the construction industry. It's been used for anything from bespoke architecture to pool lining and even cliff stabilization.
Carl Akeley was a real pioneer. His contributions to the world of engineering are truly remarkable.
At Crossrail, a pre-mixed wet concrete known as Shotcrete is pumped through a specially adapted, super-sized, automated version of Akeley's machine. At the nozzle end, high-pressure air is used to accelerate the mix towards its target.
The mixer truck will bring in the concrete to this Shotcrete robot here, which is basically a pump and a manipulator so that the nozzle man, who is this chap here, can place the Shotcrete in exactly the right place. Historically, people used to spray by hand. These machines allow you to pump up to maybe 60 tons an hour.
The technique involves rapidly spraying the freshly excavated ground with a sophisticated, fast-curing mix of shotcrete to stabilise it and form the permanent tunnel lining.
This is the Shotcrete, which is essentially a concrete mix with small aggregate. It's got these things which are like small high tensile steel fibres. They're like reinforcing bar effectively on a micro scale. I've worked on quite a lot of tunnels. This is exciting. There's a lot going on. You're always up against pressure for programme, pressures against cost, and we're changing the culture for one that is infinitely more safe than it has been historically.
With a staggering 42 kilometres of brand new tunnels now constructed, the momentous task of creating a high-tech railway is underway.
We're now in our tunnel fit-out phase. We're putting in our ventilation, all our high voltage power and signalling, and it's starting to look like how it looked when trains would run through it.
And one of the biggest jobs is laying the track itself.
On our project we have 4 different types of track. There's approximately 108 metres each section, and you've got about 47 kilometres of this across the project.
So how can the team efficiently install tens of kilometres of rail track throughout the extensive tunnels? To answer that seemingly impossible challenge, engineers draw inspiration from some of history's greatest innovators. Architectural historian Jen Mason-Garb is in California, discovering the secrets behind one of the USA's most audacious construction projects.
Today, there are over 150,000 miles of rail track across the continent. But in the early 1800s, it would have taken more than 6 months to cross the continent by horse. But all that changed on July 1st, 1862.
The signing of the Pacific Railway Act by Abraham Lincoln authorized 2 companies to build an 1,800-mile-long railroad between California and Nebraska.
This new railroad would allow people to cross the entire continent by train, a project of staggering ambition. And the 2 railroad companies had an incentive to move fast because they were paid by the mile, $32,000 per mile. And so they were off. Union Pacific starting in the east and moving west, Central Pacific starting in the west and moving east, racing across the continent to each other.
Despite the challenging terrain, Union Pacific workers were soon laying 4.2 miles of track a day. Key to this remarkable achievement was a method devised by 2 brothers, Jack and Dan Casement.
The Casement brothers had just come from the Civil War, where they served as officers, and they were in charge of laying all the track for Union Pacific. They ran this track operation with military precision.
The casement method involved creating an entire moving city. Locomotives would pull sleeping berths, dining cars and kitchens, providing everything for thousands of workers.
The key to the Casement brothers' success wasn't just in the efficiency of the workforce, but also in the really smart engineering systems that they designed. This might look like just a simple cart, but it's got a couple really cool features. Each cart had these 2 iron bars along the front and the back, which made it possible for the iron rails to slide to the edge. And then these rollers positioned the rail right into place so it could be slid right down on the ties. It saved valuable seconds, and all those seconds added up along the project really made a difference.
For the ingenious cart to be effective, the workers were split into 2 teams.
I've got this team of guys ready behind me, and we're gonna give it a shot. All right, team, ready?
The first team would use a horse and wagon to deliver the sleepers to the front of the line, laying them in place with a pair of tongs.
At the same time, another crew would be in the back, lifting the rails into position on this cart. 2 men at the front of each rail, 2 men at the back, and then this cart would be pushed to the front of the line.
Rail out.
As the cart moved into position, it was the responsibility of 2 workers at the front to grab the rail with their tongs and pull it off the cart. and then 2 workers in the back to align the 2 rails. We'd be called the heelers. And when the track was in place, the foreman would yell, "Good iron," and the cart would move forward.
Good iron. Roll ahead.
Behind the cart would be other men called strappers, who'd splice the rails together at the joins. Behind the strappers, spikers secured the rails to the sleepers with spikes.
Good.
Once the rails had all been laid, this empty cart would be pushed to the end of the line and tipped up on its side so that a new car could come behind with all new fresh rails. All right, are we ready? 1, 2, 3.
Hearing of its success, Central Pacific also adopted the technique, and work on the new line raced ahead. The casement method revolutionised track laying, and by the 10th of May 1869, just 5 years after work had started, the 2 construction crews met, and a golden spike was planted to mark the completion of the Transcontinental Railway, one of the world's greatest engineering achievements. At Crossrail, the team are taking those early pioneering track-laying methods and giving them a 21st century makeover.
Behind me is the multi-purpose gantry, and really, MPG is a real-life transformer. We have 4 of them on this project that were designed for Crossrail.
These modern-day versions of the Casement Brothers trolley cars cost £1 million each, and are the track-laying workhorses during the fitting-out stage. To begin, the MPG drags 108-metre-long sections of steel rail into position, placing them on either side of the tunnel floor.
You've got approximately 47 kilometres of long welded rail, so a large amount of track we need to install all through utilisation of the MPG.
Next, sleepers are positioned in between the rail sections.
This MPG can lift up 28 sleepers in one go and position them in exactly the correct location. Across this project, we have about 70,000 sleepers we're trying to lay.
Finally, this versatile machine lifts the rail onto the sleepers, and concrete is poured to secure it in position.
The MPGs are very versatile. They can go up and down, and they can move in and out. As you can see here, you've got one wheel up on the platform, one on the upstand. They enable us to work around this challenging environment.
Thanks to these 21st century tools, the tunnel fit-out team are well on their way to welcome the first trains through in 2018.
The MPGs are real solutions to address the complexities and the magnitude of the tasks we have working in this environment.
But building a network on time as complicated and as vast as this is one thing. To make sure the 200 million passengers expected every year use it safely will mean engineers need to once again look to the past.
This is the world-famous Coney Island, a place that's provided entertainment and thrills to New Yorkers for over 100 years.
To produce more impossible engineering. Crossrail, Europe's largest infrastructure project, is gearing up to completely change the face of travel for millions across London.
Many parts of London's public transport system are virtually full already. Any additional capacity that we can add is going to help hugely.
This £15 billion network is in the final stages of construction.
The new Crossrail trains will carry 200 million passengers in and out of London every year.
So how will engineers transport an extra 200 million passengers safely from street level to stations as much as 40 metres below ground? To answer that challenge, they would look to the uplifting work of an innovator of the past. Mechanical engineer Michael Tobias has come to a thrill-seeker's paradise in Brooklyn, New York, in search of the unlikely origins of an everyday piece of engineering.
This is the world-famous Coney Island, a place that's provided entertainment and thrills to New Yorkers for over 100 years.
Up until the 1930s, this iconic attraction was the largest in the US, with 3 parks competing to build the most daring and cutting-edge rides.
Incredible. The rides that were showcased here were truly remarkable pieces of engineering, made by ingenious inventors of their day. But there's one in particular that was more than just a funfair thrill.
In 1891, American inventor Jesse Wilfred Reno, keen to attract the attention of the New York railway companies, came up with a publicity stunt to demonstrate his new ride.
Reno's invention was a prototype of the world's first working escalator.
It may not sound exciting for today's thrill seekers, but back then it caused a sensation. Named the inclined elevator, Reno's ascending movable walkway is reputed to have carried 75,000 people in just the first few weeks.
Reno's design is a sloped walkway, very similar to how a conveyor belt works. There's 2 gears at the top and the bottom, a motor on the top, pulling the walkway up, down, and over again.
With its steep incline of 25 degrees and a 7-foot rise, Reno attached strips of wood or cleats to the treads to provide traction. And most ingenious of all, at the end of the ascent, the cleats disappeared through a reciprocal set of cone-like prongs that safely lifted the passengers' feet off the disappearing treads, enabling continuous motion. Reno's plan worked, and as a result of this publicity stunt, his invention was soon installed in New York's transport system. Elsewhere in New York, other engineers were also working on their own escalator designs.
It was here, at Macy's flagship store, where Elijah Otis, inventor of the elevator, installed one of his earliest escalators.
Instead of Reno's steady incline design, Otis's plans incorporated steps. By combining them with Reno's cleat and cone design, the escalator made for a smooth ride and safe exit.
Installed in 1927, these are thought to be the world's last remaining wooden step escalators anywhere in the world.
Each step in the escalator has 2 sets of wheels, which roll along 2 separate tracks. The upper set are pulled by the rotating chains, while the other sets simply follow behind. The tracks are spaced apart so that each step will always remain level. At the top and bottom of the escalator, the tracks level off to a horizontal position, flattening the stairway.
The steps were central to Otis's design, while the cleats on the surface of the steps and the cone plate they disappear into were central to Reno's design. These escalators stand as a testament to the engineering brilliance of the men involved and form the blueprint for all modern escalators.
Back in London, and a whopping 81 brand new versions of Reno and Otis's design are set to make this new network a step-free zone. But to fit so many, up to 65 meters in length and weighing almost 45 tons, project manager Jules Boyd and his team of engineers have had to create some engineering firsts of their own.
Here you see, this is the escalator that all of the passengers that will use Whitechapel Station will come down this. It's actually very steep, as you can see.
Hanging from the rails embedded into the tunnel roof, an especially adapted machine was used to excavate this vast cavern. But instead of digging from the top down in the usual way, limited access above ground meant the spider-like machine clawed its way upwards.
This is quite unique. This is the first escalator where the tunnel was done uphill. I'm not aware of that ever being done anywhere in this country before.
By cleverly adapting equipment to suit their unique situation, the machine could beat the effects of gravity.
very difficult to do because everything is at 30 degrees. Now, as you can see, it's very awkward to do anything on here because everything rolls away. From there to there, vertically, is about 11 meters. So everything, access is very, very difficult. So it's quite an art to see.
Thanks to the dedication of those building them, the 2,500 meters of new escalators will play a pivotal role in delivering the passengers to the platforms below. The unprecedented and ambitious Crossrail project rewrites the rules of underground construction.
When you look at it now, it's amazing to think that in a couple of years' time, this will be open, the Elizabeth line will be up and running and operational.
With over 100 million working hours already completed, the success of the largest construction project in Europe stands as testament to the inspirational innovations of the past and the ingenuity of those building it today.
To see the whole process from start to finish has just been remarkable. I mean, I'm getting towards the end of my career. I doubt I'll do another one of these, but you never know.
On the brink of completion, the enormously complex and groundbreaking Crossrail remains on track and has succeeded in making the impossible possible.
If you think of all the thousands of people that worked on this project, the billions of pounds that are spent constructing it, the challenges we've managed to overcome, I think it'll be a fantastic achievement. It's a real feat for the UK rail industry.